Okay, great. Hello, everyone. Hello, everyone. Welcome back from Thanksgiving break. I hope everyone had a delightful break. I sprained my ankle playing football, so that was suboptimal. I'm delighted to introduce Rachel Somerville. Rachel is an expert in all things physical about galaxies and the universe. She wrote an exquisite review article a couple years ago, which I refer to often and also assign to my students. Rachel is a group leader at the Flatiron Institute. She's the Galaxy Formation group leader. She has about 50 people that attend her group meeting because she is both brilliant and everyone loves her. She was previously an endowed chair at Rutgers University before going full-time to the Flatiron Institute, the CCA. Everyone should visit. Today she's going to be talking to us about galaxies and how they relate to dark matter and dark energy, and how we can use upcoming surveys to try to understand the physics that drive the evolution of the universe. I'm delighted to welcome her today. Everyone, please enjoy.
Thank you so much, Erica. Well, it's such a delight to see real three-dimensional bodies out there, and so thank you for having me. I have a real fondness for Boulder, and it's always a great pleasure to visit. We've also already had some wonderful scientific conversations this morning, and I'm looking forward to continuing those throughout the day. So without further ado, let me jump in. So the motivation to this talk today is the landscape over the next decade in astronomy, which is that the US and international communities are going to be spending billions of dollars building a suite of new facilities, both on the ground and in space, that will gather together probably hundreds of petabytes of data collectively. And our hope is that these experiments will allow us to learn about deep questions about the universe, like the nature of dark energy, the nature of dark matter, how galaxies form and evolve, etc., right? Like all that good stuff that we all want to know. But I would assert that we are not currently positioned to be able to fully exploit these data at the moment. And so it's high time that we need to grapple with this problem and start building the tools to really fully extract the maximum amount of information from these experiments. So just a couple of the kinds of experiments that you saw in the timeline on the last slide that I sort of have in mind here as particular targets for the kind of modeling I'm going to be discussing include next generation cosmic microwave background surveys, which will allow us to measure very accurately the distortion in the CMB when CMB photons pass through hot gas around galaxies, groups, and clusters. So the circumgalactic gas, the so-called thermal and kinetic Tsinaev-Zeldovich effect. Also, of course, we will be surveying most of the sky and measuring the locations and velocities of galaxies. So measuring galaxy clustering. These large galaxy surveys will also allow us to do weak lensing and galaxy-galaxy lensing studies that will probe the underlying distribution of dark matter. And then a relatively new class of experiment called line intensity mapping looks for signals of lines either from molecules like CO, or from ionized gas like C+, or from 21 centimeter from neutral hydrogen, and will allow us to map out the cold gas in the ISM of galaxies over very large areas as well. So by combining the information from these different probes, for the first time, we will be able to constrain the matter in many different components in and around galaxies simultaneously for very large volumes and out to very high redshifts. So what is the big challenge here? In order to understand the kinds of data that I've just been showing you, we need to be able to model very complex and nonlinear physical processes across a huge range of spatial scales. Also, of course, the observational effects in these different data sets are going to be quite different. They all need to be handled in confronting our models with these observations. And ideally, we'd like to ultimately obtain rigorous statistical constraints on all of these parameters in this high dimensional parameter space. So again, learn about simultaneously the matter content of the universe, as well as parameters of galaxy formation. So what, I think many of us kind of have in our mind as a goal is something like what's been done currently for the CMB primary signal, right? Like if you think about the Planck papers or WMAP papers, they have this giant corner plot that shows you the posterior. You can see all of the degeneracies between the different parameters, right? So this is what we'd love to be able to do with these new experiments, combining all of these data together. Unfortunately, we cannot do this currently using the kinds of techniques that have been used for the CMB for several reasons. One is we don't understand galaxy formation well enough, right? We think we pretty much understand the physics producing the primary signal for the CMB, not so much for galaxies. And our current ability to simulate galaxy formation physics relies on computational simulations that are extremely expensive. Another problem is that, of course, the matter density field at the time of last scattering is pretty close to Gaussian. So you might expect the likelihood to also be close to Gaussian. So you can do, standard techniques using things like Monte Carlo Markov chains to explore and constrain the posterior using a Gaussian likelihood. But in this case, in the nonlinear regime of strong galaxy clustering, we don't expect the likelihood to necessarily be Gaussian. And in fact, we have essentially no knowledge about the form of that likelihood. So in order to meet these challenges, I want to talk about some of the first steps taken by my group and my collaborators to try to work towards a solution. And to be clear, these are baby steps. These are the very first steps. This will be, I expect, at least a decade of effort to reach this, kind of holy grail that I've outlined here. But I'd like to at least talk about the principles and the direction that we're going in. So the first one is to develop what I would call a more bottom-up approach to modeling galaxy formation, so a more physics-based approach, and I'll talk more about what I mean by that. The second is to make our simulations of galaxy formation both accurate, but also much more computationally efficient. So we basically need to speed up these simulations by 5 or 6 orders of magnitude in order to do this full forward modeling simulation-based inference approach. And then the third is to develop new statistical techniques for extracting the information about both cosmology and galaxy formation from these large diverse data sets that I've outlined. So part 1 is all about how to model galaxy formation. So as you all know, we have a pretty good basic picture for how we think that galaxies form and evolve at a qualitative level. We think that initial fluctuations in the matter density field grow and collapse into dark matter halos, which cluster on large scales, that within the dark matter halos, gas accretes, cools, falls to the center of the halo, starts to form stars, right? The stars then emit radiation as massive stars, supernovae explode, dump energy and momentum into the surrounding gas, causing what we call stellar feedback. And in the very center of some, maybe all of these galaxies, perhaps a black hole forms, perhaps an intermediate or supermassive black hole forms, which can then accrete. And then, of course, that accretion can tap, again, a huge amount of energy, radiation, jets, winds, which also have a profound effect on the surroundings. So that's all it's a very nice story, right? I can say all these words, but what we need to make progress on is understanding the details of how all these physical processes actually work. And of course, if you think about the scales in this problem, so the scales of large scale clustering are tens of megaparsecs, up to 50 or so megaparsecs. while the processes involved in star formation, black hole formation, black hole accretion, black hole feedback are sub-parsec scales. So we have something like 8, 9, depending on how you count it, orders of magnitude of physical scales in this problem. And that is, of course, one of the things that makes this problem so challenging. Of course, there's also a wide array of physics that needs to be included here. We don't even really know, I think, which physical processes are essential to include to capture the main properties of galaxies, but they may include, of course, gravity, of course, hydrodynamics, thermodynamics, perhaps also magnetic fields, perhaps also cosmic rays, certainly radiation, which is not self-consistently included in almost any of our simulations right now. Okay, so that's why this is so hard. However, there has been a lot of progress over the last 5 years in creating simulations of cosmological volumes. So, 100 or so megaparsecs on a side, large enough to capture some of this large scale structure that include at least sort of the main physical processes that I've just outlined. And another nice thing is that many different groups have gone through this exercise semi-independently and made different choices about the way that they implement the physics. Many of these use different underlying hydrodynamics codes and or gravity solvers, so that we have independent constraints on how to try to solve this problem. But just to sort of show you where we are in terms of this dynamic range challenge, this is a diagram that I've adapted from a paper by Nelson et al. From 2019, showing on the x-axis the simulation volume on the top, going from smaller volumes to larger volumes. I don't know if people in the room can read this. The right edge here is 10 to the 8 cubic megaparsecs. Okay, so still kind of relatively small, actually, compared to these experiments that I was showing you at the beginning. And then down to basically, just essentially one galaxy. So then the number of galaxies is on the bottom axis here. And then the baryonic mass resolution achieved in these simulations is shown on the y-axis, where smaller numbers are at the top. So this is better resolution, higher resolution, but smaller particles or grid cell masses. And so what you can see is that we have simulations called zoom-in simulations, where we might only have a few galaxies or very small volumes simulated, but where we can achieve fairly high resolution. And in these higher resolution simulations, we can implement some of these physical processes that I was mentioning in what I call semi-resolved way. You may see what I mean by that a bit more later. In order to fully resolve these physical processes, you would have to have resolutions even better than these current cosmological zoom-in simulations. And on the other side, ideally we'd like to shoot for really over here, right? But sort of some of the current famous simulations like Illustris TNG are shown here, Eagle, Simba, etc. So you can sort of see where these lie relative to kind of where we want to be eventually. So because of this limitation in dynamic range, these current simulations that I showed you the pretty pictures from all have to implement many of the important physical processes using what are called subgrid recipes, right? So that means you have some limited resolution, and below that resolution, you can't explicitly solve the physics, so you have to put in some assumptions or some kind of scaling relations, which are often very phenomenological. So this is, as I said, an incomplete list of physical processes that have to be implemented in this way. And for this talk, so I think all of these are important to consider and to put on a more solid physical foundation. But just for illustrative purposes, I'm going to focus for now on stellar feedback. Okay, so stellar-driven winds. So let's do a little trip down memory lane, maybe not so long for some of you, to whichever course, maybe it's ISM where you study the evolution of a supernova remnant after the supernova explodes, right? So hopefully this is familiar to everyone, that you have the free expansion phase, ballistic expansion at constant velocity, and then you go into this set-off Taylor blast wave phase, which is energy conserving. And so immediately after that, the shell starts to lose energy rapidly, right? So then you go into this snowplow phase where radiative losses become very significant, and the remnant is essentially momentum conserving. And so you can see on the middle panel here that the thermal energy is dropping rapidly, but the kinetic energies is remaining more or less constant during this phase. So what's really critical is to resolve this blast wave phase. If you don't resolve the blast wave phase, and people found this out in the 1990s and early 2000s, if you just dump thermal energy into your simulation without resolving the blast wave, then it just cools away, right? The feedback doesn't do anything. Your galaxies are much too compact. Too much gas turns into stars. Everyone's very unhappy. The galaxies don't look like galaxies, right? It was like lots of wringing of hands to try to figure out how to solve this problem. So in order to resolve this blast wave, you need approximately a mass resolution of around 10 solar masses or so. So that's a few orders of magnitude away from the simulations I was showing you, or a spatial resolution of better than around 10 parsecs or so. So what to do, right? How can we solve this problem? For now, this is one of the approaches that's very commonly used in these large hydrodynamic simulations called kinetic hydrodecoupled winds. So the idea is that, okay, this blast wave is imparting some momentum. Let's kind of represent that in a schematic way by depositing kinetic energy into our gas to represent these supernova-driven winds. So there's a launch criterion, or a set of assumptions around launch, which basically is, okay, I'm going to take a particle of star-forming gas and I'm going to give it a kick. And so you have to make an assumption about how often you do that, how many particles you kick, and then how much you kick them, right? So that's basically the launch velocity. So what's typically done is there's some equation, some formula for the mass loading, right? So basically for how much gas you kick, and energy loading and metal loading that you stick in your simulations. Then the second piece is recoupling. So typically what's done in these simulations is these wind particles that have been generated still feel gravity, but hydrodynamic forces are switched off for those particles artificially until either the particle falls below a certain density or it has a certain travel time. So again, there's a set of rather arbitrary conditions that determine how long this wind particle gets to travel without feeling hydrodynamic forces, and then it's just dumped back into the surrounding gas. So again, it turns out if you experiment with different ways of doing this, that yes, it matters, it does make a difference, and so this is another arbitrary piece of these current recipes. So because you don't know, so you might have some equations like this for the wind velocity at launch, for the mass loading, and you have some parameters here that you don't know what they are, right? And this yellow thing here actually hides maybe 3 or 4 parameters, right? You can put in a metallicity dependence, you can put in whatever dependence you want for this mass loading term. So what's typically done currently, and this is an example from Lester's TNG, but this is essentially the same approach that's used by all of these groups, is to tune these parameters to match some global properties of galaxies that you'd like to match. Okay, so again, for example, let's look at this panel, which shows the stellar mass function of galaxies. These points show some measurements of the stellar mass function at redshift 0. And you can see these different colored lines, which are the result of changing the wind velocity, changing the wind mass loading, right? So you can make it go up and down, you can change the shape and find some parameters that do pretty well at matching some set now of observations that you've decided are important to match. You do have significant degeneracies, and you do it by eye, and you can't run very many of these because they're expensive. Exactly, Mitch, exactly, yes. I'm not claiming that this is a unique solution to this problem, and this is all done by eye and there's no error bars. That's exactly the point. I'm not criticizing anyone, by the way, right? Like, this was a huge step forward from making things that didn't look like galaxies. So, you know, you do what you can, but yes, there are degeneracies. So again, I do want to emphasize that after you've gone through this process of tuning to some set of observations, that there are some non-trivial predictions, if you like, or successes that are not baked in, that emerge from these simulations. For example, the galaxies cluster in more or less the right way on large scales, right? Blue galaxies cluster less strongly than red galaxies. You produce things that look a lot like galaxies, right? I mean, this was really amazing when this first kind of started to emerge from these simulations. You produce things that look like disks, you produce things that look like ellipticals in more or less the right relative numbers. And, you know, the ellipticals are in dense environments and the disks are in less dense environments. So lots of things kind of, you know, qualitatively work under this scheme. And you can ask, okay, well, what about all these different groups that did this in these different ways? Do they get the same answer or not, right? Because everyone made a bunch of different assumptions about how they did this subgrid modeling. So the answer is, it depends what you look at. So if you look at the stellar mass function, which again, remember, this is something almost everyone uses to tune. So at redshift 0, all these different colored lines are models from different simulation groups. This also shows a bunch of semi-analytic models here. This is from the review article, which is now sadly becoming out of date. So at redshift 0, yeah, they all agree really well, but that was kind of by design. Even if you go out to, and we show this in this paper by Jung et al., even if you go out to redshift 10, the stellar mass functions from many, many different simulations actually agree remarkably well, within a factor of a few, which I find amazing, actually, especially when we did it out to these very high redshifts. So that's pretty interesting. However, if you look at other quantities, many other quantities, here's one troubling example, you see much larger differences between the different simulations. So what this is showing is the power spectrum computed in the full hydro simulations, okay, so as a function of K, the usual power spectrum, relative to this power spectrum in a dark matter only simulation. Okay, so it's basically how much are the baryonic processes modifying the power on these scales. And so you can see that these different simulations, which again implemented the subgrid physics in different ways, give radically different predictions for the power spectrum, or the effect of baryons on the power spectrum, particularly on relatively small scales, right? So on sort of megaparsec and smaller scales, again, where the baryonic physics is doing a lot of work. So possible concerns we may have at this point, in addition to the one that Mitch has raised, is that these subgrid models depend on these global properties and are tuned to match global observations. So of course, their predictive power is somewhat limited. The different choices may lead to different predictions. So then you don't know which one is right. You don't even really know, like, what is the range of priors you should be considering in trying to interpret cosmological data. And even where we're matching observations, we're not really sure that we're matching them for the right reasons, right? So we could be getting the right answer for the wrong reasons. Yes, Andrew.
When you say the hydro power spectrum, you talk about the power spectrum of galaxies, and if so, what kind of galaxy?
This is just the total matter density power spectrum of all matter.
Okay, baryonic matter.
All matter.
But well, you've got dark matter there, and there's a difference between the
Yes.
power spectrum.
Yes.
By the way, you might want to repeat the question.
I'm sorry. Okay, so Andrew is asking, is this the power spectrum of galaxies? No, it's the power spectrum. It's just taking the matter, the particles in the simulation. So in the dark matter only simulation, of course, that's only dark matter. In the simulations with baryons, it's both baryons and dark matter. The baryons actually modify the distribution of the dark matter significantly. Okay. Does that answer your? Good. Okay, excellent. Yeah, of course, if you selected galaxies, they might be biased in different ways, right? Yeah. Absolutely. Okay, so obviously there are improvements we'd like to make to this approach for modeling galaxy formation, and this was the goal of a collaboration that was started at the CCA along with several collaborators a few years ago, which we call SMAUG, which stands for Simulating Multiscale Astrophysics to Understand Galaxies. And the goals of SMAUG are to develop new approaches for modeling these subgrid physics recipes that, instead of relying on phenomenological scalings and tuning, rely on a ladder of multi-scale simulations. So basically drill down until you can actually resolve the physical process of interest, try to understand how that physical process works, maybe develop an analytic model that can then be implemented in one scale up, and build your way back up to the cosmological simulations. So no more tuning. There may still be parameters in your modeling, but the parameters have to be set based on your lower rungs in your ladder, not on observations. Okay, and another one of our principles is that any kind of validation should be done in the observational plane with as full as possible and accounting for observational error. So no tuning on the stellar mass function anymore, right? We need to be validating our models in the observational space. Okay, so at the core of the SMAUG project is something we call Project Arkanstone. So the Tolkien fans may recall that the Arkanstone was Smaug's favorite treasure, right? This jewel that he really, really liked. I think this is a pretty brilliant name. So I think it was Drummond Fielding who came up with this. So this effort has been led by Matthew Smith and Drummond Fielding. And so this project is to develop a new approach for modeling both the launch and the recoupling of both stellar and AGN-driven winds. I'm only going to talk about stellar winds, but we hope to use the same approach to improve our modeling of black hole-driven outflows. So at the bottom rung of our ladder, so to speak, is a suite of simulations called TIGRIS. You can see what it stands for here on the slide, developed by Ivo Strecker and Chang-Gu Kim. So these are MHD simulations of shearing boxes, so what are sometimes called tall boxes. So they're about 500 parsecs this way and about 1.5 kiloparsecs this way, vertically. Sorry for the people on Zoom who can't see me. And so they have resolution of around a few parsecs, sort of 2 to 8 parsecs. They've done extensive convergence studies. So they can resolve these set-off Taylor blast waves from supernova explosions and measure the emergent properties of the winds driven by these supernova explosions. Okay, they also include a suite of other physics that you can read here on the slide. If you take a look at the movie here that's playing, let's focus on the middle panel, which shows the temperature of the gas. You can see that these outflows are manifestly multi-phase. So if you look closely near the midplane, and it may not be too easy to see. Hopefully you can see this blue stuff, yeah? So there's some cold material, which actually doesn't make it very high. It's sort of more like a fountain. And then you can see the hot material that makes it much, much further outside of the disk. So one thing that's very clear from studying these simulations is that if you try to represent winds with one kind of particle, you will completely fail to capture the properties of these winds, okay? So you need to treat the different phases of the winds separately, and so that's part of our approach. So we've done these simulations for these different vertical slices representing different initial conditions for the global conditions of these boxes. So different densities, different shears, we're now doing different metallicities. And so each of the points on these diagrams represents a different run of one of these tall box simulations, okay? So now we can measure explicitly these wind launch conditions that we then want to put into our cosmological simulations. But now, instead of measuring them as a function of a global property, like a global velocity dispersion or something, we're measuring this as a function of something like the local gas density or the local star formation rate density on the scale that you can resolve in your cosmological simulation. So maybe, a couple hundred parsecs or something like that, okay? And so you can see here the scaling relations for mass loading, momentum loading, energy loading, and metal loading for the cool material on the left and the hot material on the right. In the paper, we actually show the full 2D distribution, and we provide a sampler if you want to sample the full 2D distribution of the wind launch properties with temperature. You don't have to make this arbitrary division in case you're worried about that. But for simplicity, we decided to just do, for now, these two phases. And so you can see a couple of interesting things. One is that most of the mass is in the cool phase, but most of the energy is in the hot phase. Sorry, energy down here. And there is a dependence, fairly strong dependence of the mass loading on the local surface density, such that higher surface density, lower mass loading. So interestingly, if you fold this together with sort of the expected density profiles of galaxies, you get out the global scalings for the mass loading that are pretty close to what we needed to put into the cosmological simulations like illustrious TNG to get galaxy properties right. So we think, we're hopeful that this is all going to sort of work once we put it in, but now it's not tuned anymore, right? It's based on these simulations that are actually resolving the winds. Okay, so let me talk about the second piece now of the wind model, the Arkanstone model, and that is how the wind interacts with the circumgalactic material as it's traveling out. Remember, in the TIGRIS simulations, it's only going up to 1.5 kiloparsecs. So we need to understand how it propagates much further out into the CGM and possibly even out into the IGM. So fundamentally, we need to know how these wind particles exchange mass, energy, and momentum with the surrounding material, right? And we think that the predominant mechanism for this exchange is in these turbulent radiative mixing layers. So in these Kelvin-Helmholtz instabilities that form at the interfaces between cold and hot material that are in relative velocity relative to one another. They're moving relative to one another. And again, these processes are happening on sub-parsec scales. So no cosmological simulation is resolving this process or even coming close. So here, the bottom rung of our ladder is a bunch of these radiative mixing layer simulations. This was work led by Drummond Fielding, where, again, we studied many different cases of relative velocities between the cold and the hot material. So here you can see temperature, density, Mach number, cooling time, and X, Y, and Z components of the velocity. And you can see here the mixing layer that forms as the gas moves relative to one another. So of course, hot and cold on the bottom. And what Drummond found in this very beautiful work is that this surface, this interface layer, is actually a fractal. Kind of looks like a fractal, right? And so this energy loss term depends on this set of dimensionless quantities listed here. So things like the scale relative to the relative velocity and the cooling time, the ratio of the density of the cold to the hot material, and the Mach number. So you can put all these dimensionless quantities together in an expression that depends on the fractal dimension of this mixing layer. Okay, so he basically created an analytic model describing this mixing process based on these idealized simulations, but with this nice analytic theory, which I should mention, I think is very much a child of Mitch's work with Andy Fabian back in 1990. So then what Drummond has done is to develop this into a set of analytic equations describing the change in properties for an ensemble of clouds. So we've launched these wind particles, right? And we can think of each of those wind particles as being an ensemble of these very small clouds, right? These perhaps sub-parsec scale clouds. And depending on the mass of the clouds, there's sort of this competition going on where you have radiative cooling. So if the clouds are fairly large, they tend to grow via cooling, but then the clouds are also being destroyed by the mixing. So smaller clouds actually tend to be shredded and destroyed by mixing. And so their fate will be set by the balance between the cooling and the mixing. And that's in a nutshell what these long, complicated equations are describing. So now, instead of turning off the hydrodynamic forces for these wind particles, as they move through the surrounding medium, they're solving these little analytic models and asking, okay, am I growing? Do I get to keep going? Or am I destroyed and mixed back in with the CGM? Okay, so we've put both of these pieces together now. We've tested them in some sort of classic idealized wind models. They seem to be behaving very well, and we're now implementing them within an idealized isolated Milky Way-like galaxy, and then we'll be able to compare how different the predictions are from sort of the canonical Illustris TNG-like feedback model. So that is where that stands. Now, of course, there's a whole wing, tail, or leg, I don't know, of SMAUG that is focused on what I view as perhaps an even more fascinating and more difficult problem, which is, all of the above, but applied to how black holes form, how black holes accrete, how black hole feedback works. Unfortunately, I'm not going to talk about that. I could easily give a whole hour talk on this topic and on this work. Again, it's very dear to my heart. So I apologize. I know lots of people here like black holes. If you want a little taste of what we've been doing, you can check out this paper on the archive led by Kunyi Su, where we explored idealized galaxy models with jets, where we explore a wide variety of different parameters for the kinetic energy, thermal energy, cosmic ray energy, magnetic field, strength, duty cycle, opening angle, like everything you can think of with regard to jets, and studied which kinds of jets can and cannot quench the cooling flows in a 10 to the 14 solar mass halo. Also, an extremely cool paper by Daniel Angles Alcazar, where he used what's called a hyper refinement technique. So we do a zoom, we stop the zoom at some interesting point, and then we refine, we split the particles into smaller mass particles within a certain region, and we just keep doing that. So you can kind of see the scales that we're getting down to here. And we study how the gas is accreting onto the black hole using direct gravitational capture, and how that compares to commonly used recipes like Bondi-Hoyle. Spoiler alert, Bondi-Hoyle is off by 4 orders of magnitude, right? No big surprise. So we're continuing these kind of studies with more of these simulations to study different kinds of conditions. Okay, so with that, let me switch gears. Should I be aiming to end at 3:30-ish? Yeah, okay. Oh, 1:30. 1:30, sorry, my computer's on East Coast time. 1:30, good. It's okay, okay. Somehow I'm only through a third of my talk, which I don't know how that happened, but that's okay. I'll just stop when we run out of time. All right, but let's steam on to the second part, which is developing more computationally efficient models of galaxy formation. So many of you probably know about Semianalytic Modeling, which is an alternative to numerical hydrodynamic simulations, that instead of solving the equations of hydrodynamics, thermodynamics, et cetera, for particles or grid cells, sort of tracks the global flows of material between different reservoirs. So here's sort of a graphical picture where you can imagine, let's just ask, how fast is gas accreting in from the IGM to the halo, accreting from the halo into the galaxy, and how fast is it being ejected out of the galaxy or ejected out of the halo? And basically, it's just a big flow model with a bunch of ODEs that you solve to describe how mass moves between these different reservoirs. And so traditionally, for each of these flow terms, again, people have written down some phenomenological scaling relation, right? Like maybe you put in a Kennicutt-Schmidt relation for how gas turns into stars in the ISM. And then those parameters were tuned to match observations, right? Sort of similar to what I was talking about before. But what we're trying now is to instead put in these global scaling laws to reproduce the results of a particular hydrodynamic simulation. So for now, we've been using fire and illustrious TNG. There's 2 published papers on this if you're interested. And the goal is to see how well we could sort of emulate the predictions of global quantities using this much computationally cheaper technique, sort of trained on these hydrodynamic simulations. And the idea, of course, is that once we have these more physically grounded SMAUG simulations, that we could then train a semianalytic model to sort of emulate them more rapidly. So one of these studies that I want to highlight was led by Gabriel Pillai, where he compared published Santa Cruz semianalytic models with illustrious TNG. And I just want to highlight one result here. So if you consider a scaling relation, let's take halo mass versus stellar mass, okay? So you might want to consider, how well do the medians match? That's very commonly done. But then you might also want to consider what's the residual of any particular galaxy or halo from the median relation. And do the 2 techniques, full hydrodynamics versus semianalytic models, predict the same thing for whether a galaxy is sort of high or low on that scaling relation? So kind of an interesting thing. So this is still stellar mass, halo mass. For the semianalytic model for TNG, here's the comparison of the medians, and then here's the comparison of the residuals. So things that are in either of these sort of quadrants here and here are things where both techniques are predicting that the galaxy is either high or low, right? So we are quite encouraged that not only does the median match quite well, but even these residuals are showing a significant correlation. So at least for stellar mass, the 2 techniques are doing something similar. And it's also interesting that if we look at this residual of stellar mass, halo mass, and how it correlates with the halo's formation history, or the concentration parameter of the halo, which correlates with the formation history, there's a strong correlation there, which is seen in both kinds of simulations. So the galaxy's stellar mass seems to depend in a similar way on the halo formation history, again, even though the physics was done in these 2 completely different ways. All right, that doesn't work as well for other properties. So this is showing the CGM mass, so the mass of hot gas surrounding galaxies. And here the agreement is pretty terrible between the 2 methods. So this is pointing out to us a particular physical process in the simulations or in the semianalytic models that we need to fix to make it match the simulations better. One reason that this was so encouraging and so exciting is that, of course, one of our goals is to be able to predict how galaxies cluster over large scales, right? To try to make forecasts for and eventually interpret these large galaxy surveys that I mentioned. So one of the commonly used techniques for predicting galaxy clustering is called an HOD model, Halo Occupation Distribution Model, which assumes that basically the way that halos cluster only depends on their mass, okay? We know that that's not true. And if we try to use an HOD model to represent the clustering predicted by, say, illustrious TNG, a full hydro simulation, it's inaccurate at the 10 to 30% level, okay? So we know that HOD models don't accurately represent what's in hydrodynamic simulations. This work, I should mention, was led by Boriana Hajicka, who's a finishing graduate student at Harvard. So she compared the clustering, this shows the 2-point correlation function times r squared as a function of scale in the Santa Cruz semianalytic models and TNG, and found very good agreement. And even more interestingly, when we looked at a signature of what's called assembly bias, so assembly bias is basically the name for the fact that halos of the same mass cluster differently depending on some other property, right? Like formation time or concentration, okay? So what this plot is showing is the correlation function that you actually measure, let's say in TNG or in the semianalytic model, divided by the correlation function that you would get if you just randomly shuffled halos of different masses. Okay, so if there were no assembly bias, this line would just be flat at unity, right? So this plot is essentially showing you the signature of assembly bias and its dependence on scale. And you can see that the semi-analytic model is doing a very good job of reproducing the scale dependence and the degree of assembly bias that's seen in illustrious TNG, again, at a fraction of the computational cost. Okay, so in my last few minutes, let me just give you a little taste of some of the work we've started doing using new techniques for extracting information about cosmology and galaxy formation from observations. So the sort of pilot project here is called Camels. This has been led by Paco Villaspueza Navarro, Shai Genel, and Daniel Angozalcazar. And Camels is a suite of thousands of simulations, literally 2,000 some n-body and 2,000 some full hydrodynamic simulations that have been run using two different codes, two different sets of physics, so two different assumptions about subgrid physics. One, the illustrious TNG physics model, and the other one, the SIMBA model, which I haven't talked about, but again, similar yet different, right? And spanning 6 parameters, 2 cosmological parameters, so omega matter and sigma 8, and then 4 parameters that represent parameters in these subgrid recipes controlling both stellar feedback, so 2 controlling stellar feedback and 2 controlling AGN feedback. Okay, so we've done a big Latin hypercube sampling the 6-dimensional parameter space and run thousands of simulations. And the whole point of this, the whole goal of this, was to have a test bed to develop machine learning based techniques for interpreting these simulations. So on January 6th of next year, you can ask me later why January 6th, we will release this amazing data set called the Camels multi-field data set. So we're releasing the full field data for all of these many quantities that you can see here, gas density, temperature, metallicity, etc., for all of these thousands of simulations. And this will all be made publicly available for people to play with. So just 2 little highlights. There are a bunch of papers out on the archive from Camels, so feel free to go and check those out or ask me later. So let's, for just one nugget, ask the question, suppose you knew from observations the total matter density field. Okay, so just the density in some set of pixels, some set of cells, right? Here we used, I think, 256 cubed cells or something. Suppose you knew that. Can you train a neural net? So in this case, we used a convolutional neural net, pretty vanilla, to learn the value of omega matter, let's say, or the value of sigma 8. And so the answer is, so this shows the true value here of omega matter, here of sigma 8 on the right, versus prediction minus truth when we do this exercise using the neural net. So if you look at the red and the green points, this is the answer that we get if we train on the illustrious TNG-like simulations and we also test on them. Okay, so we assume, they're used both for training and testing. Then we get 2 to 3% accuracy. If we do the sort of harder exercise, if we said, well, but we know that the physics probably isn't what's in the real universe, how much does that matter? So if we train on illustrious TNG but test on SIMBA or vice versa, then we get the purple and the blue points, which is still pretty good, still, around 4% or so accuracy. And remember, that's varying all of these parameters controlling the baryonic physics very, very widely. So the neural net seems to be able to kind of marginalize over these variations in the modeling of the baryonic physics to get out these cosmological parameters. Okay, but you might say, well, but I don't know the matter density. That's not really an observable. How about, what if we had something closer to an observable? So here, this part of Camels was led by Lucia Perez, who's a graduate student at ASU, also finishing this year. So she ran another 1,000 dark matter only simulations now in a bigger box. So the main Camels simulations, I should have said, are only 25 megaparsecs on a side. They're very small. They're too small to do clustering. So she ran 100 H inverse megaparsec on a side simulations, spanning the same sort of range and cosmological parameters. And then we used the Santa Cruz SAMs to fill them with galaxies and also to vary these parameters, controlling, again, stellar feedback and AGN feedback. And we asked the same sort of question: can you train a neural net to learn from, so in this case, we used the 2-point correlation function, the void probability function, counts in cells, just those 3 things, I guess, for 4 redshifts. So that was our training data. And we asked, how well can the neural net learn all of the parameters? So both cosmological parameters and the astrophysical parameters. And it does quite well on the cosmological parameters, not so well on some of the astrophysical parameters. But then it turns out if we just ask it to learn, say, one of the parameters, if we just asked it to learn this parameter, which happens to control the radio mode AGN feedback, then it can also do quite well. So this seems very promising. And to wrap up, I just want to sort of announce, advertise a new collaboration. So this is what's called a Simon's collaboration. Ask me later if you want to know more about what that is, called Learning the Universe. And the goal of this collaboration is basically to put together all of these different pieces that I've mentioned and really take them to completion. So, really refine them, develop them fully, and do this full problem. So developing these new subgrid models for galaxy formation, both for the stars and for the black holes and the AGN, using machine learning to significantly accelerate those simulations, so to sort of emulate the simulations in rapid ways, perhaps incorporating semianalytic modeling, and then to fold those in with observational effects for galaxy surveys and for next generation CMB experiments, and do the full simulation-based inference pipeline to get out those corner plots that we want. So this will be a 4 to 8 year project involving lots of people, and I'm very excited about it. So let me wrap up there and leave you with my summary and take some questions. Thanks for your attention.
Okay, questions? Questions for Rachel?
Near the beginning, when you were showing the slides that compare all the different simulations, are the physics improving because the resolution is improving? Is that just, can you see more in some of the simulations, or can you actually put more things in as the resolution gets better? Does that question make sense? Of
Yes.
How
Yes.
does the improvement of physics and the resolution?
It totally makes sense. Yeah. Yeah. So in the low resolution simulations, you just don't know about the relevant conditions to put in the physics modeling that we know is happening. So you have to make assumptions. But once you have higher resolution, then you could actually put in the physics, the real physics, and study it. And so the idea is to learn from those higher resolution simulations where you can put in the physics more explicitly and more accurately. And again, based on something that we think we know and not an assumption. And then use that to do better when you have the lower resolution simulation. Does that make sense?
Yeah. So when you talk about the TNG model, like they have 3 different runs. How does that, like when the resolution improves, is that always included in the model?
Ah.
You can't see it?
That's a great question. So you're thinking of like, oh, so the question is, I think, tell me if this is your question. So TNG has 3 different runs at different resolutions. So there's like the 50 box, the 100 box. Is this what you're talking about? Yes, and they have very different resolution. So what you're asking is that, does that mean that the physics in TNG 50 is more accurate than the physics in TNG 300? Is that what you're asking?
And then when you say you're using TNG model, like which resolution, or how does that, what does that mean? External to TNG?
Yeah, so in TNG and in most simulations, they don't change the subgrid modeling. They don't change what physics is put in when they change the resolution. And actually one of the problems with these simulations is that they're not well converged. So you actually get a different answer when you run it at different resolutions, which is bad, right? So that's one of the goals of having more physically grounded subgrid recipes that hopefully would also be better converged, because as you change the resolution, your subgrid recipe should account for that, right?
Yes.
Does that answer your question?
That was my question.
Awesome. That was a great point, actually. Yeah.
One thing I forgot to mention also is that Rachel was on the steering committee for the fatal survey, so you can tell her how good of a job she did.
Oh, thank you. And you can ask me about that too, but
Yeah.
I can't tell you any like dirty secrets. So. Nothing too juicy.
Other questions? Maybe one. We have time for one more. Yeah.
What is the years of magnetic field?
I'm sorry, what is the what?
Like, is there a summation with magnetic field? I mean, it's at the end, so if you have magnetic field, I mean,
Yes.
most of the time you talk about hydro.
Yes. Yes. So that's also an interesting question. So for example, illustrious TNG.
What was the question?
Oh, sorry. Keep forgetting.
It's so hard.
So I think the question is, what's the role of magnetic fields in these simulations? That generally, or how important are they? Or which ones have them, which ones don't have them? So, you know, like when I showed you the panel with all the different simulations, a couple of those do have MHD. Many of them are just HD, right? And I think there's a lot of questions about the accuracy of the implementations of MHD in these large simulations. And again, you know, the magnetic fields are probably incredibly important for the actual physical processes, but that doesn't mean that they're properly incorporated in the subgrid recipes, right? So I think the answer is that we don't know how, you know, magnetic fields really affect global galaxy properties, but that's one of the things we could hope to learn from, you know, this kind of approach where we're really trying to understand the physics in the subgrid recipes. So for example, the TIGRIS simulations, that bottom rung, you know, that I was showing you, those are full MHD, and there I trust a bit more, you know, that we could learn something about the role of magnetic fields. And in fact, we are studying the role of magnetic fields in outflows and how they affect the ability of supernova explosions to drive outflows. The answer is not very much so far.
Let's thank Rachel one more time.
Fire.
That was delightful. It was great. I love it. Thank you. It was so awesome. It's like so. I was just, look at all this cool stuff, and I was so excited. Good. Good. I hope it was good. Yeah.
This was a great talk.
Oh, thank
Very
you.
inspiring.